Thank you, CSDMS, for inviting me to give this talk, and also thank you for getting me involved in this cool project. So I'm Mauro Werder. I'll be talking about subglacial drainage modeling, and this is work I've been doing with Ian Hewitt, Christian Schoof, and Gwen Flowers in Vancouver. So why should we want to model the glacier drainage system? There's a couple of reasons. One of the main one is that there is strong coupling between ice flow and hydrology. So, for example, this is a figure by Palmer showing part of the Greenland ice sheet margin, and red indicates high flow speed, and the black lines indicate likely axis of the subglacial, well, main axis of the subglacial drainage system, and there's a strong correlation. But there's other reasons why we want to model it as well. So maybe interesting bit for you guys here is subglacial erosion is coupled to sliding, which again is coupled to subglacial hydrology. So here is a cross-section through a glacier, and so how does water flow through a glacier? And the main component of this model is the subglacial drainage system. So that's drainage along the ice bed interface. And the kind of main conceptual distinction people make is between the distributed system, which is inefficient, and the channelized system, which is channelized and efficient. And the distributed system in this model is through link cavities. I'll get into them later, and then we have the channels. And then there's also an end-glacial system, which routes the water, meltwater, which is produced at the surface, through the glacier to the bed. And there's probably also a storage component within the ice. So this model I'll be presenting is a sheet flow model, so that's a distributed flow, plus a channel flow model, and then some storage and glacial routing. And the model has a name, it's called GLAD, so that's Glacial Drainage System. To model water flow, 3 ingredients are needed. First one is conservation of water mass. Second one is that water flows down the hydraulic potential gradient. So the hydraulic potential is defined as the pressure plus the elevation, so that's just rho GH. And then we use kind of empiric relation between discharge and the hydraulic potential, kind of Manning or Darcy-Weisbach type. So the discharge is proportional to minus the square root of the gradient of the hydraulic potential. And then the third ingredient we need to know how the drainage space evolves. So that means how the channel cross-sectional area and the sheet thickness evolves. And one thing to note is that unlike subaerial drainage, which probably most of you are doing this, the flow is pressurized, so these channels and the sheet is completely filled with water most of the time, and that's what we assume in this model here. So the sheet is composed of link cavities. So the dark patches are where the ice is in contact with the bed, and the white patches are where these cavities are. So water flows between these cavities, and we average over a suitably large patch of the bed to get to an average sheet thickness. And this leads to these 3 equations, the 3 ingredients: mass conservation, turbulent flow, opening, and closure. And one thing about the opening of these cavities is that these cavities form behind bedrock bumps, so ice is sliding over these bedrock bumps and will lift off on the lee of the bumps, and then the cavities close by creep closure of the ice. So that's this opening and closure term. And if we combine these 3 equations, we get an elliptic equation for phi, so the hydraulic potential, and just the ODE, namely this one here, for the drainage space evolution. Now, channel flow. So on the right, you see a cartoon of a channel. So this is the ice, here's the channel, here's the bedrock. So that's incised into the ice. And the way these channels work is that they melt open by dissipation of potential energy in the water flow. And they also close by creep closures, just like the cavities. And again, we get these 3 ingredients: mass conservation, turbulent flow law, and opening and closure. And again, combining these three, we get an elliptic equation for the hydraulic potential and an ODE for the drainage space evolution, the channel cross-sectional area. And the important thing to note is that these are one-dimensional creatures, these channels. So these equations are just valid along a line. So, so summarizing channels versus the sheet. So both closed by this ice creep closure, which tries to close in on the open spaces. The sheet opens up by this sliding over the bedrock bumps, and the channels open up by melt. And this melt opening up is actually what leads to flow localization, because the bigger a channel, the more melt there is, so bigger channels want to be bigger and capture the discharge. And even though these equations I showed you have been known for 30, 40 years, they have not really been coupled in 2 dimensions so far, because there's the problem of these one-dimensional channels. How do we couple them in a kind of a 2D model to the 2-dimensional sheet? So the way we do this is we put a network of potential channels on top of the sheet. So this is this network, and channels are allowed to form on any of the edges if they want to. And the sheet lives in between those on the triangles, and of course we need to take care for that water conservation is enforced. And so this then leads to this, this elliptic equation for the hydraulic potential needs to be solved with, well, we use finite elements both on the edges and the triangles simultaneously. And I'll just now show a few results from just a showcase of what the model can do. So one is the evolution into a steady state and how this channel network forms. And the other one I will show you coupling to ice flow on the Greenland ice sheet margin. So the first run is just on the square glacier, flatbed, parabolically shaped ice surface. So the initial conditions are 0 channels everywhere and uniform sheet thickness, and the forcing is just constant input through moulins. So point sources. So up here, the red dots are those moulins where the water is injected. The arrows indicate flow in the sheet, and blue lines indicate the channels which form. So I'll show you this animation, the time evolution. So we start with 0 channels everywhere. We see how the flow in the sheet kind of goes downhill, and then channels start to form, basically joining the dots where water input happens, and you see that water is drawn towards the channels most of the time. So that's because the channels are at a lower pressure than the surrounding sheet, and thus drawing the discharge from the sheet. And then we reach a steady state. And the same simulation visualized slightly differently. Now I show contours of the hydraulic potential. So you can kind of, if you're kind of landscape evolution modelers, you can kind of think of those similar to contours of the elevation and how these are influenced. So as channels form, there's steep drop in hydraulic potential at the head where the channels form, and then channels will carve valleys into the contours of the hydraulic potential most of the time, but there's also channels which lie on ridges of the hydraulic potential, and these are kind of too small to, well, to have enough discharge, so they're leaking out discharge continuously. So you can kind of almost think of it like a stream sitting on a ridge, leaking discharge onto the sides. So the second thing I'd like to show is that coupling to ice flow. So there's a two-way coupling between hydrology, subglacial hydrology, and ice flow. So increased water pressure leads to increased sliding, and that in turn leads to increased cavity opening rate. And there then we have a negative feedback to water pressure. So and the canonical example for this are so-called spring events. In spring, when the first meltwater pulse reaches the bed of the glacier, you get a speed up of 200–300% in some cases of the ice flow. So this is for the margin of the Greenland ice sheet. It's for the year 2011. It's forced with a local regional climate model, random moulins, and we have surface and bed DEM. And here is the animation I'll show you On the left, contours of the hydraulic potential again, and you'll see the channels forming. On the right, the flow speed of the ice, and you'll also see the channel system forming. And down here is a time series of the forcing, so that's the total melt input into the whole domain. And you'll see a vertical bar running through it as we advance through the season of 2011. So at the beginning, that's just background winter flow speed. And then as melt starts to happen, pressure increases, flow speed also increases, but then as the channels start growing headwards, in these areas the pressure decreases again and have lower flow speeds there. And then at the end of the season, except for kind of drainage, meltwater pulses, it slows down again and we reach background winter flow velocities again. So yeah, at the beginning of the season, speed up at the margin and kind of speed up in big areas, but then where channels form, it slows down again. It's kind of mid-season here, and except when there's another drainage meltwater pulse, it speeds up again and then slows down again at the end. And I'd like to finish up with a quick comparison to subaerial drainage. So there's some similarities. So we have both distributed and channelized flow in both instances. Arborescent networks form, and the channels shape the hydraulic potential. So in the case of landscape evolution, the landscape is shaped by the erosion of the channels, and in this instance, the channels decrease the pressure, so thus that's how they deform the hydraulic potential. But there's differences, so it's pressurized flow for the subglacial drainage. The time scale is much different. For landscapes to evolve is thousands of years, whereas here we're talking of a month. And the channels, some of them actually can lie on ridges as well, which is not really what you can see in subaerial drainage. And I think I'll just pop up here these conclusions, and if you have any questions. Yeah, thank you.
Well, that's very interesting. Is there a characteristic space? Well, firstly, do the channels grow and reach some kind of an equilibrium spacing where there's this resorption of all the small channels in the beginning? And if they do, is there a characteristic spacing, and what's it depend on?
I'm not sure what the characteristic spacing depends on, but yeah, I think there is. So depending on varieties of input and parameters. And yeah, you also get kind of differences that for some parameters, mainly if the sheet is very conductive, you get just a few channels and generally straight channels. And if the sheet is very unconductive, then you get much more arborescent network, which has much more finer structure. And I think that's kind of, yeah, again, similar in landscape evolution, where you have more or less fine channels forming.
Very interesting talk. I just have one question. How sensitive is the location of the channel and the shape of them are relative to the initial condition, like the hydraulic potential? If you run your simulation for a second time with varying it slightly, are they going to form again at the exact same locations, or?
Yeah, so I think one of the big questions in kind of that general frame is also, we use kind of a random mesh, so randomly, well, unstructured random mesh. So and between different meshes, you'll get different channel configurations, especially if you have no topography guiding them. But once you get to most real-world examples, the topography will usually be a strong enough influence to kind of localize the channels. And then once, depending on what initial conditions you start with, if you have a channel already established in one point, it can take quite a bit of effort to kind of move it to maybe a kind of more energy lower point, but the movement is maybe not happening.
This is great. I have two kind of gently related questions, basically about the bed. Did you put till in there, and can you form nye channels?
Well, so at the moment it's a hard. The conceptual model is for a hard bed sliding over these bumps, but I think it should be applicable to a soft bed as well, because you will have similar dependence and kind of opening and closure rate dependent on the sliding. And night channels, which are channels incised into the bed as opposed to into the ice, no, we can't do them yet. But it would be nice to have kind of really a soft till underneath, and maybe sediment erosion, and you could form channels that way too.
So thank you very much. Let's give a hand. Our next speaker